Hello, let's have a look at how sound is represented in binary in a computer. This students often find quite a difficult topic, and I can understand why, because it's really hard to get your head around how sound works. We take it for granted that we can hear constantly and we can talk and people can hear us, but the physics behind it is remarkable. As a computer scientist, we focus on the binary side of things, but to understand this topic, I think you have got to get a rough sense of how things work in real life. So let's start there with some content which isn't essential for GCSE computer science. It might be for physics, but it's useful for understanding the computer science parts of this topic. So I'm talking right now into a microphone. You are hearing this via headphones or speakers. How does that all work? Well, real life sound is caused by particles vibrating in the air. And as they're vibrating, this creates waves. So if we were to see this, if we could see the particles in the air moving as I'm speaking, my voice box is creating these vibrations which are spreading out through particles vibrating. And this GIF labels a wave we can see. We don't typically visualize waves in this way because it's hard to visualize. So typically what we do is draw these waves on two axes. And typically these axes are the y-axis being displacement, so the height of your wave, and typically the x-axis is time, because we have a wave which has an amplitude. The amplitude is the height of a wave that changes over time. So as I'm speaking, I'm creating waves which are getting picked up by the microphone and converted to binary in the computer. But how can we interpret these waves? Well, if I was to draw a wave which maybe starts quite tall and then gets a bit shorter, what is that meaning in terms of how we hear it? Well, this tallest bit would have the loudest volume. This would be the loudest thing you would hear here because it's got the tallest amplitude. That's the height of our wave. That's why sometimes the y-axis is written as volume, maybe with decibels as your unit. And the smaller the amplitude, the quieter it will be. The other main factor at play is how high-pitched or low-pitched the sound is. How is that determined? Well, that's determined based on the frequency. And in a non-technical way, this is basically how squished our wave is. So if part of this wave is really, really spread out, that would be quite deep, quite low-pitched. Whereas if I had part of it which was the same height, so the same volume, but a lot more squashed together, that would be a lot higher pitched than this lower pitched part. That's why if you slow down video footage, you put it in slow motion, that's why all the voices go a lot deeper. And if you sped it up, it goes a lot higher. That's because when you make it faster, the waves get squashed together, so it goes high pitched. Now, are they going to ask you any of what I've just said on a GCSE computer science paper? No, but it's important to roughly understand how sound waves work so that we can apply some of the actual computer science content, which we can start now, because the whole purpose of this is to convert this sound wave into binary. We have to store sound in a computer somehow. How do we do this? How do we convert it to binary? Well, the whole goal here is to convert the amplitude at different points in time to binary. We have got a complication here in that real life sound is analog data. What that means is it is a continuous wave. So here is a simple wave. This is a smooth wave. There are no breaks in this wave. Sound is constantly being created. We can constantly hear stuff. Some of it is quiet. We can constantly hear stuff. It's a continuous waveform. If we were to zoom in to this wave and zoom in and zoom in and zoom in and zoom in, we're never going to see a break. It's a perfectly smooth, perfectly continuous wave. And that means really there are an infinite number of values we could be storing. And that will not sound good because we don't want things to be infinite. Things being infinite is a really bad thing because a computer can only store data that has a finite range of values. Finite means there are a limited range of possible values, which we need because we only have limited memory space. So how do we go from analog data, which is what we actually hear in real life, to what we call digital data? That's what the computer can actually use. Well, there's a process called sampling, which converts it from analog to digital. We want it to go from analog to digital. Digital data is discrete data. That's the opposite of continuous. Continuous has no breaks. Discrete, we've got a fixed range of values which are separate. So how does sound sampling work? Well, the device doing this is a microphone. A microphone is recording measurements of the amplitude of the sound wave that it detects at regular time intervals. Each one of these measurements is converted to binary and stored. This is a very set definition I've given you here, which you sort of need to learn because it's quite a common exam question. How does a microphone sample sound? Well, this is how. That doesn't make sense unless you've looked at an example. So let's put another graph up and let's perform some sound sampling ourselves. Well, this is not going to be super accurate because the scale is nowhere near what it'd really be for a sound wave. So we are just simplifying here, but let's just draw a potential analog sound wave. So this is analog because it is continuous. There are an infinite range of possible values here. And I need to convert this into binary. Well, let's follow this definition. So I'm recording measurements of the amplitude, the height of my sound wave at regular time intervals. So I need to first of all decide what are these time intervals. An interval is a length of time. At what length of time do I want to be recording samples? A sample is a measurement of the height. Well, let's say I'm doing this once per second. So I'm doing 1 per second. So every second, I'm going to take a measurement of the amplitude. So at 1 second, the height is 7, I would say. So 7 meters. Again, meters is crazy for real sound, but let's just pretend the height is 7. So what I need to do is I need to record that I've taken a sample at 1 second. The height at this point is 7. Let's put 7 in binary because that's what we're actually trying to do. Well, I've got 0 to 7 on my scale here. This is 8 combinations in total. So let's represent this height with a 3-bit binary number. So what is 7? Well, 7 is going to be 1, 1, 1. I then need to take my next sample. Well, it's always at regular time intervals, so I've got to wait another second. So at 2 seconds, the height, I reckon, is, about 6. So at 2 seconds, the height is 6. What's 6 in binary? It's 1, 1, 0. At 3 seconds, the height looks to be, it's not quite there, but is roughly 2. At 4 seconds, I've got a bit of an issue because 4, it's between 0 and 1 on my scale. And we don't know how to convert fractions into binary. So we're a bit stuck here. I need to decide whether I want to go either 0 or 1. That is where sampling has a limitation, right? Because analog is a nice smooth wave and we're converting it into a discrete wave, we're going to occasionally lose some important data because I'm converting an infinite range of values into a finite range of values. So here, I'm going to go for 1 as opposed to 0. So 1 in binary is 0, 0, 1. But we'll see in a second how this may affect the sound. I've got similar at 5 seconds to at 5 seconds, it is kind of between 5 and 6. It's closer to 5. So let's go with that. 1, 0, 1. And let me finish this for all of these 12 seconds of sound we've got here. So there we go. I've completed this sampling process. I've taken these regular measurements of the height. If I remove all the stuff I've got on my graph here, we're left with what really a sound file is on a computer. Just a bunch of binary being stored back to back. Each part is representing a different amplitude of our sound wave. So if I wanted to hear my sound file, it needs to get played out via a speaker. A speaker converts it from digital data into analog data again. And we can visualize this by plotting these points back on this graph. So at 1 second, we have a height of 7. The next time interval, I've got a height of 6. At 3, it's 2, and so on and so on. When we see the points on the graph, we can see this is clearly digital discrete data. It's not a continuous line like the analog data was. But a speaker will need to convert it back into real sound, which is analog. And we can visualize this by effectively connecting the dots, which I'll do as best I can here. There we go. And we can immediately see it's quite a jagged line here. That's not only my bad drawing, but if I was to put back in the original line, which I drew a few minutes ago, you can clearly see the green line, which is the sampled version, deviates from our original. And this is proving the fact that we can never replicate an analog wave perfectly. The digital version is never going to be quite as smooth or quite as perfect because we just cannot replicate an infinite range of values. Sampling is trying to get close to the analog wave. Here, parts of it are quite close. So in the parts where it's quite close, it would sound pretty similar to the original. Then the parts where it deviates, it would sound louder than it should do, or the pitch would be a bit wrong, or the sound would be a bit different. So it wouldn't be quite as accurate as the original analog version. And as we look at in the next video, how frequently we take these samples is really important for determining how close our digital version is to our analog version. And also how many binary digits we store each sample is also another key factor in how close our digital wave is to the original analog one.